Hi, my name is Jim. Current direction, kind of an important concept. In the late 1800s, physicists performed an experiment and they put a spoon or some other utensil in solution with a silver bar, and they connected it to a source, a battery if you will, and the positive terminal of the battery was connected to the bar of silver and the negative terminal to the spoon. And what they found was that the silver molecules eroded from the bar and plated themselves onto the spoon. So what they thought was that this was the flow of current, electron current, and that turns out to be quite incorrect. What was actually flowing here is ions, and an ion is a charged particle. For example, suppose I take a silver atom which is being acted upon by a voltage source and subtract an electron from it. Well, it's missing one. It has a net positive charge, and what we know is that unlike charges attract, so the silver molecule, the ion, migrates over to the spoon, picks up an electron in the process while plating, that is, sticking to the spoon. So, conventional current came out of the 1800s. It's not correct, but it's been adopted by the industry. So that's what we use. Some years ago I read that 95% of textbooks are conventional current. Now if you learned on electron current, it's very easy to switch. So let's just take a little simple circuit here. We have a battery or a cell, and electron current is flowing from negative through the load to positive, and this current is indicated by an E with a negative sign or just an E to tell the reader that they're talking about electron current. If you do not see that, you assume that it's conventional current. So we have a source of energy and a load, and it's easy to treat conventional current just by drawing an arrow from the positive side of a source into a load. Now the industry had adopted this to the point of taking the symbol for a light emitting diode. Which direction does the arrow point in? The direction that conventional current flows, which will cause light to come out of the diode. In this particular part, it won't flow backward anyway. An NPN transistor, here we have a terminal called an emitter with an arrow on it. What direction does conventional current flow? In the direction of the arrow. So it's very, very well embedded in the industry of conventional current flow. So let's take for an example, and you've heard me speak frequently of sources and loads and kind of explore that a little bit. And I think this is an interesting example. Here we have a cell phone, and we have the battery here acting as a source, and then the cell phone electronics, transmitter, receiver, screen, and any other peripheral stuff that may be inside of it, a compass module or whatever, acting as the load. So if the cell phone's turned on, the battery discharges through the load and runs all of the stuff inside the phone. Sooner or later, the chemical energy inside the battery becomes depleted, and the cell phone electronics will no longer run. Fortunately, this is a secondary battery, secondary cell, which means it can be recharged. Primary cells, like alkaline cells, cannot be. Once their chemical energy is expended, you throw them out, buy a new one. But in a secondary cell, you can charge it, and when you put it in a circuit to charge it, this higher voltage here might be a wall cube, and current will now flow into the positive terminal of the cell battery. Here in discharge is flowing out, and charge is flowing in. Now what's happening in here is that the electrical energy flowing in is reconstituting the chemical energy, replacing it. The electrical energy is being converted into chemical energy so that it can go from charging into discharging and running the phone again. Now every time you charge a battery, you kind of wear it out a little bit. So it has a finite number of charge-discharge cycles until it's more or less not useful anymore, which means the time that you could run your cell phone will become smaller and smaller and smaller. In this case, the battery is a source. In this case, it's a load. Conventional current flows into a positive. It's a load. If it flows out of a positive, it's a source. So if we take another relatively simple circuit here, I've got a 12-volt battery, and this is powering a light-emitting diode, and it has a resistor in series with it to limit the current, and in most cases that is necessary. If you remember, we talked about the characteristic curve of a diode, and it looks something like this in quadrant 1. So if we have a voltage which is fairly high, we have a really high current flow. And typically if you get above 20 milliamperes in here, you're pushing it a bit. The last explosion I had in the basement is I was working with an infrared light emitting diode, and my driver on that shorted out, the transistor I was driving it with, and exploded the lead, and the lens of it's buried in the wall behind me somewhere. I never did find it. And I wasn't wearing safety glasses, by the way. So things can go bad, and when they do, you have to be prepared for it. And I'm just kind of taking a little jog over here into the aspects of safety. Things do explode. So what we can say about this, if the current flows from positive to negative, it's a load, and if it flows from negative to positive, it's a source. Pretty straightforward. What we know here is we're plus, plus, minus, minus, and a little bit later we'll be discussing Kirchhoff's voltage law, which basically says is that the sum of the sources has to equal the sum of the loads regarding voltage. So we can kind of see that here. Now with resistors, in this case it's an explicit resistor, whereas before we talked about resistors as being a component of the filament of a light bulb, say, or an undesirable characteristic in a piece of wire perhaps. So if we have a physical resistor, we have to kind of learn how to figure out what the value is and do it in a manner that we don't have to get a piece of equipment out, an ohm meter, and measure it. So the industry has come up with a color code, and the color code is written down here, black, brown, and so forth, and the significant numbers that they represent is next to it. So what we're going to do is take a look at the 3-band resistor plus a tolerance band and see if we can make these numbers make sense to us as far as what the resistor value is. And the first example I've chosen is a strange one, but nevertheless it's a good place to start. So we have a resistor here, an example one, and the bands are red, orange, and black, and this bands will be toward one side so you'll know. And what we can say about red is it has a value of 2, and orange has a value of 3, and then the third band, the multiplier, black, has a value of 0. So in the multiplier, the color tells you how many zeros you add to the number. Black means you're adding 0 zeros to the number. So writing this down, I have a 2, a 3, and 0 zeros, which means the resistance is 23 ohms. Now suppose this was red, orange, and brown. Well, brown has a value of 1. So I would add 1 0 for the third digit, and that then would be 230 ohms. Let's take another example. In this case we have blue, red, and green. Blue is equal to 6, red is equal to 2, and green is equal to 5. So we write down 6, 2, and we append to that 5 zeros. So breaking that down a little bit so we can read it easily, we see that this comes out to be 6,200 K, or 6,200 million ohms, which would be 6,200 K, or 6.2 megohms, and this is a capital M and the omega symbol there. Now, we can express this in any of these forms and be mathematically correct, but when we talk the language, especially on tests and so forth, this is the one you want to use. This is what the industry uses with the prefix on that of mega. So let's take a look now at a 4-band resistor. And before we do that, let me kind of step back a little bit. I don't want to forget this. This is why. They have 0 ohm resistors also. Now you might say, why ever would you have a 0 ohm resistor? And the reason is it has a resistor's footprint. that means the lead spacing of a resistor, be that a, I don't know, say an 1/8 watt or a 1/4 watt, or maybe even a surface mount. And what it's used for is to jumper PC boards without having to use a physical piece of wire. So if we have a printed circuit trace and another printed circuit trace, and we do not want these two to intersect each other, we can put pads here, that is circles, what you see on this, put a 0 ohm resistor between it, and then this will bypass, that is to say, not connect this circuit with this circuit. Now you might say, why not use a jumper wire that's insulated? And there's nothing wrong with that, except a human would have to put it in. With this, an automatic pick and place machine that stuffs the circuit boards can pick up a 0 ohm resistor, stick it in the board, solder it, done. So if you find something that looks like this, 0 ohm resistors are alive and well, and that's what their purpose is. Continuing, let's take a look at a 3-band resistor with the consideration of tolerance. Now, our concerns here on tolerance are going to be if the 4th band, and this is not the 4th significant band, it's the tolerance band, is silver, it means that the value of the resistor, as displayed by the color values, has a tolerance of plus or minus 10%, and a gold band means that it's plus or minus 5%. In the old days, they used to have no band, which was 20%, and the process right now is that it's hard to find a resistor that isn't at least 5%. So how does all this work? Well, we're going to take our nominal resistance here, which is 6.2 megohms expressed as e to the 6th for entry into a calculator, and multiply it by the tolerance as a decimal, which would be 0.05, and that gives us 310E3. In other words, the value of the resistor is 6.2 megohms plus or minus 310 kiloohms. So if we add the 310 kiloohms to a 6.2 megohms, we get 6.51 megohms, and if we subtract it, we get 5.89 megohms. So what that means is that if this resistor is to be considered good, the resistance has to be in this range. Nothing more difficult than that. Now, you might think, well, it's easy enough to do. Take an ohm meter, it's got 2 leads on it, display, put it across the resistor, tells you the value. Suppose we have a circuit that the resistor is placed in, and this is a 2-transistor amplifier circuit, and we need not concern ourselves with anything here except to note that this resistor is connected to other stuff in the circuitry. And this other stuff can be in parallel with resistors. So that means is that the ohm meter is going to have a small battery inside of it. It forces a current through the resistor, measures a current, and displays that current as a resistor value. If we've got shunt pass, parallel pass here, this resistor is going to measure lower than it actually does. Hence, we might be thinking this resistor is bad, and it's not. Now, to measure something that's in circuit, you can lift one of the leads, get rid of all the parallel paths, and measure it that way. But always beware that if you measure it in circuit, that you may have parallel paths and make it look lower than it is. Also, never, ever measure resistance with the power on. So that's one of the cautionary things here. Now another way to troubleshoot, if that's what we're doing here, is if you have this circuit that's broke and another circuit that isn't, is you can measure this resistor and compare it to the other one. And if they're reasonably close, you can assume that the resistor is good. Next, take a look at a 4-band resistor, and the tolerance band is over here. It's not shown, so we can kind of get started here. So we've got these colors, orange is 3, green is 5, blue is 6, and red is 2. And in this case, the last band, again, is the multiplier. So if we want to find the value here, we'll write down 3, 5, 6. 2 is the multiplier, so we're going to put 2 zeros after this. So the value of that would be taking our decimal point from here and moving it over to this point, 35.6 kiloohms. Now to figure out the tolerance, we do exactly the same thing before, depending upon the tolerance band, and figure out what the highest and lowest value is, and then the resistor value's actual measured value should fall within that band. Now, if a resistor is, say, 1% or 0.5%, it's typically stamped in words on the resistor. So there's no color code, per se, for a 1% or a 0.5% or something like that, where precision is really needed. Now, how do we remember color codes? Well, there's an awful lot of phrases that you can use to remember it, and it is important to remember it. Many, many times in lab experiments, students end up with the wrong value of resistor. They go to a drawer that says 4.7K, pick out a resistor, put it in the circuit, and it's not 4.7K. Somebody else misfiled it. It's the college's fault? No, it isn't. Student needs to know the color code, and they need to look at that before they put it in the circuit. You don't believe anything out of a drawer. You don't get a box in the mail with electronic parts in without verifying you got the right part. So it's important to know the color code, and one of the phrases that I found, which isn't too bad, some of them can be pretty bad, is better be right or your great big venture goes wrong. Better be right or your great big venture goes wrong. And then the first digit of each word in this phrase represents the color of the color code. So the first B is black, and that's going to be 0, easy enough. Second B is brown, 1, red is 2, or orange, 3, your, Y, yellows, 4, and so forth. So it's a good idea to memorize this or some other phrase so that you know the color code. Because it's a shame to waste 20 minutes trying to get a circuit to work when you put the wrong part in it. It's just a waste of time. You know, you're not learning anything except next time, check the color code. So that'll conclude for now. This is going to be followed by a American wire gauge chart, which relates to the gauge size relative to the current carrying capacity. And I state in that it's inverted. In other words, the lower the number, the more current it can carry. But be sure you note that. So that'll conclude for this, and thank you for watching.